Look up tonight on a clear night, far from the lights of any city, and you will see somewhere between 2,000 and 3,000 stars with your naked eye. It feels like a lot. It feels like abundance. But that scattering of light is almost nothing, a single grain of sand from an entire beach, because the galaxy those stars belong to, the Milky Way, contains something closer to 400 billion stars, and our galaxy is one of an estimated 2 trillion galaxies in the observable universe, which means the total number of stars within reach of our telescopes is a number with more than 20 digits in it. A number so large that there are more stars in the observable universe than there are grains of sand on every beach and in every desert on Earth, by a factor of thousands. Around a great many of those stars we now know are planets, not a rare few. Planets are the rule, not the exception. On average, every star you see hosts at least one world, and a significant fraction of those worlds sit in the temperate zone where liquid water can exist, where the chemistry that led to you and me is at least possible. When you run the arithmetic, the galaxy alone should contain billions of potentially habitable planets, many of them billions of years older than Earth, orbiting stars that were already ancient when our sun was still a cloud of collapsing gas. And so a question arises, simple to ask and maddening to answer. A question that has haunted physicists and astronomers and philosophers for the better part of a century. A question that gets sharper and stranger the more we learn rather than softer. If the universe is so vast, so old, so full of worlds, then where is everybody? That is the Fermi Paradox. And tonight we are going to take it apart piece by piece, follow it down every corridor it opens, and confront what it might be telling us about our place in the cosmos and about our future, because, make no mistake, this is not an idle puzzle about aliens. The answer to this question, whichever answer turns out to be true, has staggering implications for the survival of our species. And by the end of this video, you may find that the silence of the night sky is one of the most unsettling facts you have ever seriously considered. Before we begin, 3 quick things. If you are new here, subscribe, because this channel is built for exactly this kind of journey. Long, slow, deeply researched explorations of the universe and our place in it. The kind of thing you can put on at night, close your eyes, and let carry you somewhere else. Hit the like button because it genuinely tells the platform this is worth showing to other curious minds. And leave a comment telling me where in the world you are watching from and what time it is there. Because I read every single one, and there is something I love about knowing the same quiet question is being asked right now, in a bedroom in Manila, a kitchen in Lagos at 3 in the morning, a parked car outside a job someone is dreading in Ohio. Wherever you are, whatever hour it is, stay with me to the end, because the possible answers to this question get progressively stranger and more profound as we go, and the last few are the ones that will keep you up tonight. Now settle in. Let us begin with the man whose name the paradox carries. In the summer afternoon when the whole thing supposedly began with a single offhand sentence over lunch. The year is 1950. The place is the Los Alamos National Laboratory in New Mexico, the birthplace of the atomic bomb. And among the physicists there is a man named Enrico Fermi, one of the towering intellects of the 20th century, a Nobel laureate who built the world's first nuclear reactor. A man so quick and so precise in his thinking that his colleagues, themselves among the smartest people alive, spoke of him with a kind of awe usually reserved for forces of nature. Fermi was famous for a particular talent, the ability to estimate the answer to almost any question, however enormous or seemingly unanswerable, using nothing but logic and a few reasonable guesses. How many piano tuners are there in Chicago? How far would the blast wave of a bomb travel? These back-of-the-envelope estimates, done in his head in seconds, became legendary and are still taught to physics students today as Fermi problems. On this particular day, Fermi was walking to lunch with a few colleagues, and the conversation, as it often did among physicists in that era of flying saucer sightings and science fiction, turned to the possibility of extraterrestrial life and interstellar travel. They talked, they joked, they sat down to eat. The conversation moved on to other things. And then in the middle of the meal, apropos of nothing, out of a silence, Fermi suddenly asked, "But where is everybody?" The table laughed because everyone somehow understood immediately what he meant, even though he had said so little. He meant that if the galaxy is as old and as vast as we believe, and if intelligent life is anything other than vanishingly rare, then the galaxy should long ago have been visited, colonized, filled with the evidence of other civilizations, and yet we see nothing, hear nothing, have never found a single confirmed trace of anyone but ourselves. Fermi, in his lightning way, had done the estimate in his head and arrived at a contradiction between what should be and what is. That contradiction is the paradox, and it has never been resolved. To understand why Fermi's lunchtime question is so much heavier than it sounds, you have to understand the sheer scale of the mismatch it exposes. And to do that, we need to talk about time, because the numbers involved in time are, if anything, even more staggering than the numbers involved in space. The universe is 13.8 billion years old. Our Earth is about 4.5 billion years old, which means the universe existed for more than 9 billion years before our planet even formed. And during all those billions of years, generations of stars were born and died, forging in their cores the heavy elements that life requires, seeding the galaxy with carbon and oxygen and iron, building the raw material for worlds and for biology long before the sun ignited. There were stars with planets, potentially habitable planets, billions of years before Earth was a glimmer. If even one of those ancient worlds gave rise to intelligent life just a fraction of the time before we did, they would have had an almost unimaginable head start, not centuries, not millennia, but millions or even billions of years of advancement over us. And here is where the paradox tightens its grip, because you might think that crossing the galaxy would take so long as to be effectively impossible, and therefore the silence is easily explained by distance. But run the numbers, and the opposite is true. Suppose a civilization develops the ability to travel between stars, not at the speed of light, which may be forever out of reach, but at a modest fraction of it, or even far slower. Suppose they send out probes or ships to the nearest stars, and those colonies, once established, eventually send out their own ships to the next nearest stars, and so on, each new outpost becoming a launching point for the next wave. This is not exotic technology. This is just patience and replication. The same strategy that let a single species of ape walk out of Africa and populate every continent on Earth. When you model this kind of expansion mathematically, even with conservative assumptions, even with slow ships and long pauses between waves, a single civilization could colonize the entire Milky Way in something like a few million to a few tens of millions of years. That sounds like a long time, and by human standards it is. But against the age of the galaxy, it is nothing. It is a blink. If the galaxy were a single year old, the time it would take one civilization to spread across all of it would be measured in hours, which means that any civilization that arose even a few million years before us, a mere eye blink in cosmic terms, would have had more than enough time to be here in this solar system, on this planet, long before humans existed. The galaxy should already be full. It should show the fingerprints of others everywhere we look. Their probes should be in our asteroid belt. Their structures should orbit distant stars, betraying themselves in the light we collect. Their radio chatter, or the exhaust of their engines, or the waste heat of their megastructures, should light up our instruments. And yet, when we point our most sensitive telescopes at the sky, when we scan billions of stars across every wavelength of light, when we listen across the radio spectrum for any signal that bears the mark of intention, we find nothing. Silence. A silence so complete and so total that it has its own name among the people who study this. They call it the Great Silence, and it is not the comfortable silence of an empty room. It is the uncanny silence of a room that, by every reasonable expectation, should be crowded, and yet appears to be empty. Imagine walking into a vast city that should be teeming with millions of people, and finding the streets bare, the windows dark, the machinery humming but unattended, no footprints, no voices, no one. You would not feel reassured by the quiet. You would feel a creeping dread, because the emptiness would demand an explanation, and every explanation you could think of would be disturbing in its own way. That is the emotional weight of the Fermi Paradox. It is not merely that we have not yet found aliens. It is that our absence of contact, given everything we know about the age and size and fertility of the universe, seems to require something to be badly wrong with our assumptions. And the candidates for what might be wrong range from the mildly surprising to the genuinely terrifying. To organize our thinking, it helps to have a framework. And in 1961, a young astronomer named Frank Drake wrote down an equation that has become one of the most famous in all of science. Not because it gives us an answer, but because it gives us a way to ask the question properly. The Drake equation is not really an equation in the usual sense. It does not spit out a number you can trust. What it does is break the enormous question, how many communicating civilizations are there in our galaxy, into a chain of smaller questions, each of which we can at least try to estimate. It goes like this. Start with the rate at which stars form in the galaxy. Multiply by the fraction of those stars that have planets. Multiply by the average number of planets per star that could support life. Multiply by the fraction of those where life actually arises. Multiply by the fraction where life becomes intelligent. Multiply by the fraction of intelligent species that develop technology capable of broadcasting their presence across space. And finally, multiply by the length of time such a civilization remains detectable before it dies, or falls silent, or moves beyond our ability to notice it. String all those factors together, and you get an estimate of how many detectable civilizations should exist in the Milky Way right now. When Drake and his colleagues first sat down to guess at these numbers, they arrived, depending on their assumptions, at estimates ranging from a handful to many thousands of civilizations sharing our galaxy at this very moment. Thousands. And that was just our galaxy, one of 2 trillion. So the Drake equation, rather than resolving the paradox, made it worse. It gave a rigorous structure to the intuition that the galaxy should be crowded, and it made the silence even harder to explain, because now the emptiness was not just a vague impression, but a violation of a specific, quantified expectation. And that is the true shape of the Fermi Paradox. On one side, the mathematics of abundance, the overwhelming numerical case that we should not be alone. On the other side, the brute observational fact that, so far as we can tell, we are. The rest of this video is an attempt to reconcile those two sides, and every serious attempt falls into one of 3 broad camps. The first camp says they are not here because they were never there, because something makes intelligent life far rarer than we assume, perhaps so rare that we are alone in the galaxy, or even in the observable universe. The second camp says they are out there, but we cannot see them for reasons ranging from the technical to the philosophical to the frankly disturbing. And the third camp, the smallest and in some ways the most provocative, says that they were here or are here, and we simply have not recognized them or have not been told. We are going to walk through all 3, and I want to be honest with you about something from the start. Some of these explanations are comforting, some are neutral, and some are among the darkest ideas ever proposed in the history of science. Ideas that suggest the silence is not empty, but ominous, that the quiet is a warning we are too young to understand. So let us begin with the first and in some ways the most fundamental possibility, the one that would upend everything we assume about our own significance. The possibility that the reason we have found no one is that, against all the odds, against all the vast arithmetic of stars and worlds, there simply is no one else to find. The idea that we might be alone sounds, at first, almost absurd. How could a universe this enormous produce only one instance of intelligent life? But absurdity is not an argument. And when you look closely at the actual chain of events that led from lifeless chemistry to a species capable of building radio telescopes, you begin to see just how many improbable steps had to line up in exactly the right order, and how easily any one of them might have failed. This line of thinking is often called the rare earth hypothesis, and its central claim is that while simple life might be common in the universe, the specific combination of conditions required for complex, intelligent technological life is so extraordinarily unlikely that it may have happened only once, here on our world. Consider first the problem of how life begins at all, the transition from non-living chemistry to the first self-replicating molecule, a process scientists call abiogenesis. We do not know how it happened. That is worth saying plainly because it is often glossed over. We have theories, we have suggestive laboratory experiments, we have plausible environments like deep-sea hydrothermal vents where the necessary chemistry might have unfolded, but we have never observed life arising from non-life, and we do not know how probable or improbable the event actually was. It might be that given the right conditions, life springs into existence almost inevitably, a natural consequence of chemistry running long enough. Or it might be that the origin of life required a coincidence so precise, a molecular accident so unlikely, that it happens perhaps once in a galaxy or once in a universe. We simply do not know, and until we either create life in a lab or find a genuinely independent second example of it somewhere else, we cannot know. This single unknown, sitting right at the base of the entire question, is enough to make everything above it uncertain. But suppose life does begin. Suppose simple, single-celled organisms arise. On Earth, this appears to have happened remarkably early, within a few 100 million years of the planet cooling enough to have liquid water, which some take as evidence that the origin of life is easy. But then something strange happens, or rather, something strange fails to happen for an extraordinarily long time. For roughly 2 billion years, life on Earth remains simple. Nothing but single-celled organisms, bacteria and their relatives, floating and dividing, generation after generation, for a span of time longer than the entire history of complex life that followed. 2 billion years of nothing but slime. And then once a single momentous event occurred, an event so improbable that as far as we can tell, it happened exactly one time in the entire 4 billion year history of life on this planet. One simple cell engulfed another, and instead of digesting it, formed a partnership with it. A merger that produced the complex cell, the eukaryotic cell, the kind of cell that all animals and plants and fungi are built from. The kind of cell with a nucleus and internal machinery, and the capacity to grow large and specialize and cooperate. Every complex organism that has ever lived, every tree, every dinosaur, every human being descends from that single ancient merger, that one accident that never repeated. If that event was as unlikely as its singular occurrence suggests, then even on worlds where life arises easily, it might get stuck at the level of pond scum forever, never taking the leap to complexity, and a galaxy full of life could still be a galaxy empty of anyone to talk to, and the improbable steps keep coming. Even after complex cells arose, it took another billion years or more for them to organize into multicellular creatures. And even then, for most of the history of animal life, there was nothing resembling intelligence in the human sense. Consider the dinosaurs, who ruled the Earth for 165 million years, a reign more than 800 times longer than the entire existence of our species, and who never in all that vast expanse of time developed technology or language, or the capacity to ask where everybody is. They were magnificent, successful, dominant, and they were going to keep being dominant indefinitely until an asteroid roughly 10 kilometers across struck the Earth 66 million years ago and wiped them out in a geological instant. And here's the unsettling part. That catastrophe, that random rock falling from the sky, was very likely a necessary precondition for our own existence. The extinction of the dinosaurs cleared the ecological stage and allowed the small, scurrying mammals that survived to diversify, to grow, to eventually give rise to primates and to us. Without that asteroid, the age of reptiles might still be underway, and there might be no one on Earth wondering about the silence of the stars. So our existence depended not only on a chain of improbable biological innovations, but also on a specific sequence of cosmic accidents, catastrophes, that happened to fall in exactly the right way to clear a path for us. Change any link in that chain, and we are not here. And there is more, so much more, when you start to catalog the conditions our planet enjoys that may be far rarer than they appear. We have a large moon, unusually large relative to our planet, formed by a titanic collision early in Earth's history. And that moon stabilizes the tilt of our axis, preventing the wild climate swings that would occur if our planet wobbled freely. We have a molten iron core that generates a magnetic field, an invisible shield that deflects the solar wind and prevents our atmosphere from being stripped away into space, as very likely happened to Mars. We have plate tectonics, the slow churning of the planet's crust, which recycles carbon and regulates the climate over geological time, acting like a planetary thermostat. We orbit a stable, long-lived, well-behaved star, not too large and hot and short-lived, not too small and prone to violent flares. We sit at just the right distance for liquid water, in a galactic neighborhood that is calm, away from the dense and radiation-soaked galactic core, where nearby supernovae and gamma-ray bursts might sterilize any world that tried to nurture life. Take all of these factors together: the moon, the magnetic field, the plate tectonics, the stable star, the safe neighborhood, the right distance, the improbable biological transitions, the fortunate catastrophes, and multiply their individual improbabilities, and the number you get for the likelihood of a world like ours, with a species like ours, becomes very small indeed. Small enough, the rare Earth proponents argue, that we might genuinely be the only technological civilization in the galaxy, perhaps even in a large volume of the universe around us. If this is the answer to the paradox, then the silence is not ominous at all. It is simply the honest reflection of a lonely truth. We are alone because the road from chemistry to consciousness is so long, so narrow, and so treacherous that almost nothing ever walks all the way down it. And if that is the case, then this small blue world carries something almost unbearably precious, the only known instance of the universe waking up and looking at itself, and our responsibility to protect it becomes absolute. Let us go back, now that we have surveyed the whole landscape, and dig much deeper into the individual pieces of the puzzle, because each factor in the great question hides its own universe of subtlety, and the details are where the real understanding lives. Return to the Drake equation, that chain of multiplied probabilities, and let us take its factors one at a time, slowly, and see how much our knowledge has changed since Drake first scribbled it down in 1961, because the transformation has been extraordinary, and it cuts in more than one direction. The first factor concerns the rate of star formation, how many new stars the galaxy produces, and here our knowledge has grown precise. The Milky Way forms, on average, a handful of new stars every year, and has been doing so for billions of years, which is how it accumulated its hundreds of billions of stellar residents. This factor is no longer a wild guess. We can observe star formation directly, watch stellar nurseries glowing in the infrared, count the newborn suns emerging from clouds of gas and dust, and the number is solid. The galaxy is a fertile place, steadily manufacturing the stellar furnaces around which life might gather. The second factor concerns the fraction of stars that have planets, and this is where the most dramatic revolution in the entire subject has occurred. A revolution so recent that Drake himself lived to see it unfold. When Drake wrote his equation, we did not know of a single planet orbiting any star other than our own sun. Not one. For all we knew, planetary systems might be freakishly rare, our solar system a cosmic accident, and the entire question of alien life might founder on the simple absence of other worlds to host it. That uncertainty persisted for decades. And then, in the 1990s, everything changed. Astronomers detected the first planets orbiting other sun-like stars, and once they knew how to look, the discoveries came in a flood that has never stopped. We now know of thousands of confirmed planets beyond our solar system, and the statistical analysis of these discoveries has delivered a verdict that would have astonished Drake. Planets are not rare. Planets are ubiquitous. Essentially, every star you see in the night sky hosts at least one planet, and many host several, so that the number of planets in our galaxy alone runs into the hundreds of billions, perhaps more than a planet for every star. The galaxy is not a sparse scattering of lonely suns. It is a teeming abundance of worlds, more worlds than there are stars, an almost incomprehensible profusion of planets of every conceivable type. And this single discovery has massively strengthened one side of the paradox, because it means the stage for life is set not in a few rare places, but very nearly everywhere. The third factor asks how many of those planets could actually support life. And here we enter more uncertain and more fascinating territory. Traditionally, scientists have focused on the habitable zone, that band of orbital distances around a star where temperatures allow liquid water to exist on a planet's surface. Not so close that the water boils away, not so far that it freezes solid. This zone is sometimes called the Goldilocks zone because conditions there are like the porridge in the fairy tale, just right. And when we count the planets that fall within their star's habitable zone, the number remains enormous. Billions of potentially temperate worlds in our galaxy alone. But our understanding of habitability has expanded dramatically in recent years, and in ways that make the universe seem even friendlier to life, or at least to the possibility of it. We have discovered that liquid water need not sit on a planet's surface, warmed by a nearby sun. It can exist in vast, hidden oceans beneath layers of ice, warmed instead by the internal heat of a world, by the friction of gravitational tides needing a moon as it orbits a giant planet. In our own solar system, far outside the traditional habitable zone, in the cold outer darkness, there are moons that harbor oceans of liquid water beneath their frozen shells. Oceans that may contain more water than all the oceans of Earth combined, kept liquid not by sunlight, but by the gravitational churning of their parent planets. The moon Europa, orbiting Jupiter, almost certainly hides such an ocean. So does Enceladus, a small moon of Saturn that vents plumes of water vapor into space through cracks in its icy crust. Plumes that spacecraft have flown through and sampled, finding the chemical ingredients that life requires. If life can arise in these hidden oceans, warmed from within, sealed beneath ice, then the number of potentially habitable environments in the universe multiplies enormously, because such places need not huddle close to a star at all. They could exist around cold, dim stars, or in the frigid outer reaches of any planetary system, or even on worlds wandering the galaxy with no star at all. Rogue planets cast out of their birth systems, drifting alone through interstellar space, and yet still warm enough, deep beneath their frozen surfaces, to host liquid water and perhaps life. The universe, the more we learn, seems to offer more places for life to gain a foothold than we ever imagined, not fewer. And this too sharpens the paradox, because it widens the base of the pyramid, increases the number of worlds where the story could begin, and makes the silence at the top all the more puzzling. But it is the factors beyond mere habitability that remain the great unknowns, the places where the equation dissolves from science into speculation. And it is precisely those factors, the origin of life, the emergence of intelligence, the survival of civilization, that we discussed as the possible locations of the Great Filter. We can now count the worlds with growing confidence. What we cannot yet do is say what fraction of those worlds actually wake up, and until we can, the equation will remain a frame for our ignorance rather than a formula for our knowledge, a beautiful scaffolding around a void we have not yet filled. But the rare Earth hypothesis, comforting or lonely as it may be, is only one way to explain a low number of civilizations, and it leads directly into one of the most important and most chilling ideas in this entire subject, an idea that transforms the Fermi Paradox from an astronomical curiosity into a question about our own survival. The idea is called the Great Filter, and once you understand it, you may never look at the empty sky the same way again. The Great Filter is a concept proposed by the economist Robin Hanson, and it begins with a simple observation. Somewhere along the path from dead matter to a galaxy-spanning civilization, there must be at least one step that is extraordinarily hard to pass, a bottleneck so narrow that almost nothing makes it through. We know this must be true, because if every step were easy, the galaxy would be full, and it is not. So there is a filter somewhere, a barrier that stops the vast majority of potential civilizations from ever reaching the stars. The only question, and it is the most important question you will ever consider about the future of your species, is where that filter lies. Is it behind us, or is it ahead of us? Think of the entire journey as a series of gates. Gate 1, the formation of a habitable planet. Gate 2, the origin of simple life. Gate 3, the leap to complex cells. Gate 4, multicellular life. Gate 5, intelligence. Gate 6, technology. Gate 7, the survival of that technological civilization long enough to spread across the stars. The Great Filter is whichever of these gates is so nearly impassable that it accounts all by itself for the emptiness of the galaxy. And here is the crux, the fork in the road that determines whether the silence is good news or a death sentence. If the Great Filter is behind us, if the nearly impassable gate was one of the early ones, the origin of life, or the emergence of complex cells, or some other transition we have already miraculously made, then we are among the rare survivors, the improbable few who cleared the barrier, and the road ahead may be relatively open. In that case, our loneliness is a badge of triumph, evidence that we have already done the hardest thing. But if the Great Filter is ahead of us, if the early gates were actually easy and common, and the nearly impassable barrier is one of the later ones, the survival of a technological civilization. Then we are in mortal danger, because it would mean that countless civilizations before us reached roughly our level of development, and then, without exception, hit a wall they could not climb, and were destroyed, or collapsed, or extinguished themselves every single time, before they could spread beyond their homeworld. It would mean that the reason the galaxy is silent is not that intelligence is rare, but that intelligence is lethal, that something about the trajectory of technological reliably leads to their end, and that we are hurtling toward that same wall, unaware, with the accelerator pressed to the floor. This is why the philosopher Nick Bostrom, who has thought as deeply about these questions as anyone alive, made a statement that sounds backwards until you understand it. He said that if we ever discover simple microbial life on Mars, or in the oceans of Europa, or anywhere else in our solar system, it would be terrible news. Because it would mean that the origin of life is easy, common, a gate that many worlds pass through, and if life is common, but the galaxy is still silent, then the great filter cannot be at the origin of life. It must be somewhere else, and the more early gates we discover to be easy, the more the filter is pushed forward, toward us, toward our future, toward the one gate we have not yet passed, the gate of long-term survival. Every discovery of life beyond Earth, in Bostrom's logic, is a discovery that the deadly barrier lies ahead rather than behind, and that our odds of surviving it are, if the silence is any guide, essentially zero. This is the dark heart of the Fermi Paradox, the possibility that the emptiness we observe is not a sign of our uniqueness, but a preview of our fate, that we are looking out at a galaxy full of the silent graves of civilizations that were once as hopeful and as busy and as convinced of their own permanence as we are, and that failed, all of them, at the same hurdle we are now approaching. And what might that hurdle be? What could be so reliably fatal that it stops every technological species, without exception, before it can escape its home star? The candidates are not comforting, because we can see the seeds of most of them in our own history, right now, in the newspaper, in the world around us. The most obvious candidate is self-destruction through technology itself. The same intelligence that lets a species build radio telescopes also lets it build weapons capable of ending itself. Our own species developed the ability to destroy its entire civilization within a few decades of developing the ability to broadcast its existence to the stars. And we came, on more than one occasion during the Cold War, terrifyingly close to doing exactly that. Closer than most people realize, with the fate of the world resting on the judgment of individual human beings in moments of crisis and misunderstanding. Perhaps that is the filter. Perhaps every civilization, upon reaching a certain level of technological power, gains the ability to destroy itself before it gains the wisdom to avoid doing so. And the window between those two capabilities is a gauntlet that no one in the entire history of the galaxy has ever crossed. Or perhaps the filter is subtler, slower, less dramatic than nuclear fire. Perhaps it is the tendency of an intelligent species to consume its planet's resources faster than it can replace them, to alter its own climate and environment in ways that undermine the very stability that allowed it to flourish, to foul its own nest so thoroughly that its civilization collapses under the weight of the consequences before it can reach the stars. We are, at this very moment, conducting a live experiment on exactly this question, changing the composition of our own atmosphere, straining our own ecosystems, and we do not yet know whether we will pass this test or fail it. Perhaps this is the filter, and perhaps every civilization faces some version of it. And perhaps the reason the galaxy is silent is that the qualities that make a species capable of technology, aggression, expansion, relentless consumption, competition, are the very same qualities that doom it once that technology becomes powerful enough. The traits that get you to the gate are the traits that prevent you from passing through it. Let us return to the very foundation of the entire question, the single most mysterious step in the whole long chain, the transition from lifeless matter to living thing, because everything else, every civilization, every signal, every silent hunter in the dark forest depends on this one event having happened somewhere. And we understand it so poorly that our ignorance here alone could account for the entire paradox. How does life begin? What actually happens when a world crosses a line from chemistry to biology? From molecules that merely react to molecules that reproduce, that carry information, that evolve. This is the problem of abiogenesis, and it is one of the deepest unsolved problems in all of science, sitting at the intersection of chemistry and biology and physics. And the honest state of our knowledge is that we do not know the answer, though we have learned enough to appreciate how difficult the question is. Life, at its most basic, requires a molecule that can make copies of itself, and that can occasionally make imperfect copies, so that variation exists for natural selection to act upon. On Earth, this role is played by a sophisticated molecular machinery involving the famous double helix that carries our genetic code, along with an entire supporting cast of proteins and enzymes and cellular structures, all working together in a coordinated dance of staggering complexity. But that complexity is the product of billions of years of evolution. It cannot have been there at the start. The first living thing must have been far simpler, a single self-replicating molecule perhaps, arising by chance from the chemical brew of the early Earth. And the great mystery is how such a molecule could have assembled itself from non-living ingredients. Because even the simplest self-replicating molecule is a marvel of chemical organization, far too complex to expect it to spring together by pure random chance in any reasonable span of time. Scientists have proposed many possible pathways, many possible environments where the necessary chemistry might have unfolded. Perhaps it happened in warm little ponds, as Darwin himself speculated, shallow pools where organic molecules concentrated and reacted under the energy of sunlight and lightning. Perhaps it happened at the deep-sea hydrothermal vents, where superheated mineral-rich water gushes from the ocean floor and creates natural chemical gradients that could have powered the first metabolic reactions, sheltered from the harsh surface environment. Perhaps clay minerals served as templates, their crystalline surfaces organizing organic molecules into the patterns from which life could emerge. Perhaps the first genetic molecule was not the double helix we know today, but a simpler cousin, capable of both carrying information and catalyzing its own replication. A molecule that later handed off its duties to more specialized descendants. Each of these ideas has evidence in its favor and difficulties against it, and the truth may involve several of them, or none, or something we have not yet imagined. Laboratory experiments have shown that many of the building blocks of life, the amino acids that make up proteins, the components of genetic molecules, can form spontaneously under conditions that might have prevailed on the early Earth, or in the depths of space, or on the surfaces of asteroids and comets. We have found these building blocks in meteorites that fell to Earth from space, and in the clouds of gas and dust between the stars, which tells us that the raw ingredients of life are not rare, that the chemistry that leads toward life is happening all over the universe in countless places all the time. But the gap between having the ingredients and having life itself remains vast and unbridged. We can make the bricks. We do not yet know how the bricks assembled themselves into the first living house. And until we do, we cannot say whether that assembly is easy, happening readily wherever the ingredients gather, or whether it requires a coincidence so improbable that it happens perhaps once in a galaxy or once in a universe. There is a fascinating idea that sidesteps part of this problem, or at least relocates it, called panspermia. The notion that life did not originate on Earth at all, but arrived here from elsewhere, carried across space on comets or asteroids or drifting dust, seeded onto our young world from some other place where the first spark had already been struck. If panspermia is true, then life on Earth might share a common origin with life elsewhere. All of us descended from some single ancient beginning, scattered across many worlds by the debris of cosmic collisions. It is an intriguing possibility, and there is nothing impossible about it, since we know that rocks are indeed blasted off planets by large impacts and can travel between worlds, and that some microbes are astonishingly hardy, capable of surviving the vacuum and radiation and cold of space for long periods. But panspermia does not actually solve the origin of life problem. It only moves it. If life came to Earth from somewhere else, then life still had to originate somewhere on that other world, by some process we still do not understand. Panspermia can explain how life spread, but not how it started, and the fundamental mystery remains. What all of this means for the Fermi Paradox is profound. If the origin of life is easy, a natural and near inevitable consequence of the right chemistry running for long enough, then the universe should be drenched in life, every suitable world a garden, and the base of the Great Pyramid is enormously wide, which makes the empty silence at the summit all the more disturbing and pushes the great filter forward toward the higher gates, toward intelligence and technology and survival, toward our own uncertain future. But if the origin of life is hard, a fluke so improbable that it has happened only rarely in all the vastness of the cosmos, then perhaps the filter lies here, at the very beginning, and we are rare not because intelligence is hard to achieve, but because life itself is hard to start, and the galaxy is quiet simply because it is, for the most part, sterile. Its billions of habitable worlds sitting empty, warm and wet and ready, waiting for a spark that almost never comes. We do not know which of these is true. It is perhaps the single most important thing we do not know about our place in the universe. And the answer, when we find it, whether by creating life in a laboratory and proving it easy, or by searching 1,000 worlds and finding them all barren and proving it hard, will reshape our understanding of everything, of ourselves, of our future, of how alone we truly are. Suppose life is common. Suppose that across the galaxy on countless worlds, the spark has been struck, and oceans teem and continents crawl with living things. Even granting all of that, we arrive at another gate, another possible filter, and it is one that we tend to underestimate because we are on the wrong side of it to see it clearly. The gate is intelligence itself, and the question is whether the kind of intelligence that builds radio telescopes and asks about the silence of the stars is a natural destination of evolution, something life tends toward given enough time, or whether it is a bizarre and unlikely accident, a fluke that happened exactly once in the 4 billion year history of life on Earth and might happen almost never anywhere else. There is a powerful temptation to assume that intelligence is inevitable, that evolution, given enough time, will always produce creatures like us, because intelligence seems so obviously useful, so clearly advantageous, that surely natural selection would favor it wherever it could arise. But this assumption deserves serious challenge, and when you challenge it, it begins to look shaky. Consider first that life existed on Earth for something like 4 billion years, and for all but the last tiny sliver of that time, there was nothing remotely resembling human intelligence anywhere on the planet. Life was abundant, diverse, successful, spreading into every environment, evolving into millions of forms of staggering ingenuity, and yet not one of those forms, for billions of years, developed the kind of abstract reasoning, language, and technological capability that our species has. Intelligence of our kind is not a common outcome of evolution. It is, on the evidence of our own planet, an extraordinarily rare one, achieved a single time in 4 billion years, by a single lineage under a specific set of circumstances that may never be repeated. Consider also that intelligence, the humankind, is metabolically enormously expensive. Our brains consume a fifth of all the energy our bodies use, despite being a small fraction of our body weight, a ravenous organ demanding a constant supply of fuel, and building and maintaining such an organ is a costly evolutionary gamble that does not always pay off. For most creatures, in most environments, a large expensive brain is not worth the cost. A shark does not need to ponder the stars. A beetle does not need calculus. Evolution does not aim at intelligence, does not strive toward it, does not regard it as a goal. Evolution simply favors whatever survives and reproduces in a given environment. And for the overwhelming majority of organisms across the overwhelming majority of environments, human-style intelligence is not the winning strategy. It is an expensive luxury that pays off only under peculiar and perhaps rare conditions. Think of the dinosaurs again, dominant for 165 million years, filling every ecological niche, evolving into a dazzling array of forms, and never once producing a species that built a tool more complex than a nest, or asked a question more abstract than where the next meal might be. If intelligence were an inevitable destination of evolution, 165 million years should have been more than enough time for the dinosaurs to reach it, and they did not, and there is no sign they were even headed in that direction. It took a catastrophe, the asteroid, to end their reign and clear the way for the mammals, and even then, intelligence did not appear immediately or inevitably. It took another 60 million years and a very specific chain of circumstances before one particular lineage of primates, under the pressures of a changing African landscape, began the strange journey toward the kind of mind that could eventually look up and wonder. There is a counter-argument worth acknowledging, which points to the phenomenon of convergent evolution, the tendency of evolution to arrive at similar solutions independently, again and again, when those solutions are useful. Eyes have evolved separately dozens of times across the history of life, because the ability to detect light is so valuable that many lineages stumbled upon it. Flight has evolved independently in insects, in birds, in bats, in the extinct flying reptiles. Perhaps the argument goes, intelligence is similarly convergent, similarly likely to be discovered again and again by evolution because it is similarly useful. And we do see glimmers of high intelligence in creatures other than ourselves, in the problem-solving of crows and octopuses, in the social sophistication of dolphins and elephants and other great apes. Perhaps intelligence is bubbling up all over the tree of life, and given enough time, more than one lineage would cross the threshold into technology. This is possible, and it offers some hope that intelligence is not a one-in-a-galaxy fluke. But there is a crucial distinction to draw between intelligence in the broad sense, the cleverness we see in many animals, and the specific, cumulative, technological, culture-building intelligence that our species alone possesses. The kind that lets knowledge accumulate across generations, that builds cities in mathematics and radio telescopes. That specific kind of intelligence has emerged exactly once. And even if many creatures are clever, the leap from cleverness to civilization may be the true bottleneck, a gate through which, on our planet, only one lineage in all of history has ever passed. And notice something that should give us pause. Even our own passage through that gate was not smooth or certain. There were other human species, other intelligent hominins, who lived alongside our ancestors and then vanished. The Neanderthals and others, creatures nearly as capable as ourselves, who did not survive. Our own emergence into technological civilization hung by threads, dependent on climate and chance, and the razor-thin margins by which one struggling population of a few thousand individuals happened to survive and spread, rather than dying out like so many others. Intelligence, even once it appears, is fragile, precarious, easily extinguished. And the fact that we made it through, that we are here at all, may be far more improbable than our comfortable sense of inevitability suggests. If the intelligence gate is narrow, if the leap from living world to technological civilization happens only on a tiny fraction of the worlds where life arises, then here perhaps is the filter, and the galaxy is quiet, not because life is rare, and not because civilizations destroy themselves, but because life, though common, almost never wakes up all the way, almost never crosses that final threshold from mere living to knowing, from existing to understanding. And we are among the rare few, perhaps the only ones in this whole quadrant of the galaxy, in whom the universe has, against all the odds, opened its eyes. Let us step back from the abyss for a moment, because the great filter, terrifying as it is only one family of answers, and there is an entire second camp of explanations that does not require anyone to be rare or doomed at all. This second camp accepts that the galaxy may indeed be full of life, full of civilizations, perhaps even full of intelligence, and instead asks a different question. What if they are out there thriving, abundant, and we simply cannot see them for reasons that have nothing to do with their scarcity and everything to do with the sheer difficulty of one mind reaching another across the gulfs of space and time? And when you examine those difficulties honestly, you find that they are formidable, so formidable that the silence might be entirely explicable without any civilization ever having failed or died at all. Begin with the most basic obstacle, the one so obvious that it is easy to underestimate. Distance. The distances between stars are not merely large. They are large in a way that human intuition is fundamentally incapable of grasping, and no analogy quite does them justice, though we will try. The nearest star to our sun, Proxima Centauri, is about 4¼ light years away. That means the light we see from it tonight left its surface more than 4 years ago, traveling the entire time at 300,000 kilometers per second. the fastest speed anything in the universe can move. To put that in human terms, the fastest spacecraft humanity has ever built, if aimed at Proxima Centauri, would take tens of thousands of years to arrive, longer than the entire span of recorded human history, longer than the time since we painted the walls of caves. And Proxima Centauri is our next-door neighbor, the closest star of all. The galaxy is 100,000 light-years across. A signal broadcast from the far side of the Milky Way, traveling at the speed of light, would take 100,000 years to reach us. Which means that if a civilization on the other side of the galaxy sent us a greeting at the moment our species was first learning to control fire, that greeting would only be arriving now. Space is not just big, it is a barrier made of time itself, because to look across space is to look into the past, and to send a message across space is to speak to a future so distant that the speaker may be long dead before the listener is even born. This single fact, the marriage of vast distance and finite light speed, dissolves a great deal of the paradox on its own. Even if the galaxy contains thousands of civilizations, they are spread across 100,000 light-years of space, and, crucially, across billions of years of time, and the chance that any two of them happen to overlap closely enough, in both space and time, to detect one another, may be vanishingly small. Consider the timing problem in isolation, because it is more devastating than the distance problem and far less appreciated. Our species has existed for a few 100,000 years. Our civilization, in the sense of agriculture and cities, for about 10,000, and our ability to broadcast our presence across interstellar space through radio waves leaking into the cosmos for barely more than 100 years. 100 years against a galactic history of 13 billion. If you imagine the entire history of the galaxy compressed into a single calendar year, then the whole span during which humanity has been capable of interstellar communication amounts to the last quarter of a second before midnight on December 31st. A quarter of a second. Now imagine that every technological civilization has a similarly brief window of detectability, a flicker of radio noise lasting perhaps a few centuries before they either fall silent or destroy themselves, or move on to communication methods we cannot detect, or simply lose interest in shouting into the void. If those flickers are scattered randomly across billions of years, then the odds that two of them, ours and someone else's, happen to be lit at the same moment, close enough to see each other, become heartbreakingly small. The galaxy could have hosted 1,000 civilizations, each one blazing brightly for a few centuries and then going dark. And if none of their windows overlapped with ours, we would perceive nothing but silence, and we would be entirely wrong to conclude that we are alone. We would simply be alone in time, arriving at the party either too early or too late, finding the room empty not because no one came, but because everyone who came has already left, and everyone else has not yet arrived. This is why that final factor in the Drake equation, the length of time a civilization remains detectable, is so decisive and so haunting. If civilizations last a long time, blazing away for millions of years, then the galaxy should be full of overlapping signals, and the silence is hard to explain. But if civilizations are ephemeral, if the detectable phase of a technological species is brief, a candle flame that flares and gutters out, then the silence is exactly what we should expect, and it tells us something sobering about our own longevity. Perhaps the reason we hear nothing is that the speaking phase of a civilization is simply short, that intelligence is loud for only a geological instant before it either transcends the need to broadcast or ceases to exist, and that we are currently living through our own brief flare, our own quarter second of noise with no way of knowing how much of it remains. But distance and timing are only the beginning of the reasons we might fail to detect a galaxy full of neighbors. Because even if a civilization is out there right now, close enough and contemporary enough to reach in principle, there remains the enormous problem of whether we would recognize their signal, even if it were pouring down on us this very moment. We have been searching seriously for a little over 60 years, since Frank Drake first pointed a radio telescope at two nearby sun-like stars in 1960 and listened for anything that sounded artificial. That effort, now known broadly as the search for extraterrestrial intelligence, has grown enormously in sophistication, scanning millions of stars across vast stretches of the radio spectrum. And yet the honest truth is that we have barely begun. One vivid way to grasp how little we have searched comes from the researchers themselves, who calculated that the total volume of the cosmic search space we have examined across all the decades of listening is roughly equivalent in proportion to scooping a single glass of water out of all the oceans of Earth and finding no fish in that one glass, concluding that the oceans contain no fish. We have sampled almost nothing. The galaxy is unimaginably vast. The number of possible frequencies and times and directions to search is beyond staggering, and our instruments, powerful as they are, have skimmed only the thinnest sliver of the whole. It may simply be that the signal is there, has always been there, and we have not yet had the sensitivity or the coverage or the luck to stumble upon it. Absence of evidence, as the saying goes, is not evidence of absence, especially when you have examined only a single glass of water from an entire ocean, and there is a deeper problem lurking beneath the technical one, a problem not of sensitivity, but of imagination. When we search for other civilizations, we search for signals that look like the kind of signals we would send using the technology we happen to have invented in the last 100 years of our particular history. We listen for radio waves because we discovered radio. But radio is a very young technology even for us, and it is entirely possible that any civilization more than a few centuries ahead of us has long since abandoned it, moved on to methods of communication we have not imagined and perhaps cannot imagine. Methods that might be flowing through this room right now, undetectable to us because we do not know how to listen. The way a person shouting in a language you have never heard on a frequency your ears cannot register would pass you by completely. To assume that aliens communicate by radio is a bit like an isolated tribe, assuming that any distant civilization must communicate by smoke signals and scanning the horizon for smoke and concluding from the absence of smoke that they are alone, when in fact the sky above them is thick with radio and satellite and fiber optic traffic they have no means of perceiving. Our search may be fundamentally provincial, limited not by the absence of signals, but by the narrowness of our own conception of what a signal could be. This connects to a broader and more unsettling idea, which is that a sufficiently advanced civilization might be not just hard to detect, but genuinely incomprehensible to us, so far beyond our frame of reference that we would not recognize their presence, or their works, or their communications, even if we were staring directly at them. We tend, almost helplessly, to imagine aliens as versions of ourselves, a little smarter, a little more advanced, but fundamentally recognizable, creatures with ships and cities and desires we would understand. But consider the gulf between us and a civilization even 1,000,000 years older, a trivial span in cosmic terms. 1,000,000 years ago, our ancestors were not yet human. Project 1,000,000 years of progress forward at anything like the pace of the last few centuries, and you arrive at capabilities that would appear to us as pure magic, indistinguishable from the powers we attribute to gods. Such beings might have transcended biology entirely, shedding their fragile organic bodies for something else, machine intelligence perhaps, or forms of existence we have no words for. They might live at speeds of thought so fast or so slow that communication with us would be like a human trying to converse with a mayfly or with a mountain. They might have restructured themselves or their environments in ways that would look to us like natural phenomena, so that we could be surrounded by the evidence of their existence and mistake all of it for the ordinary workings of physics. When we look at a strange, unexplained, astronomical object and reach first for a natural explanation, as good scientists rightly should, we may in some cases be looking at the artifact of a civilization so advanced that its engineering is invisible to us, camouflaged not deliberately, but simply by its incomprehensibility. This is sometimes called the idea that any sufficiently advanced technology is indistinguishable from nature, a twist on a famous saying, and it suggests that the universe could be full of the works of others, hiding in plain sight, dismissed by us as background, as noise, as the mere behavior of matter, because we lack the framework to recognize intention on a scale so vast and so alien. Think of an ant crawling across a highway. The ant is surrounded by evidence of a staggeringly advanced civilization. The road itself, the cars, the entire infrastructure of a technological species, and the ant perceives none of it as such. To the ant, the highway is just a hard, flat region of the world. The cars are just occasional dangerous weather, and the intentions and inner lives of the beings who built it all are not merely unknown, but unknowable, forever beyond the ant's capacity to conceive. We flatter ourselves that we are the observers, the searchers, the ones doing the looking. But it is entirely possible that in the cosmic scheme we are the ants, crawling across works we cannot comprehend, and that our failure to find anyone is not a failure of the universe to contain other minds, but a failure of our own minds to recognize them. And if that is true, then the search for signals we would understand may be doomed from the start, not because there is nothing to find, but because the finding requires a leap of comprehension we have not yet made, and perhaps cannot make until we ourselves have crossed some of the same thresholds that separate us from them. This brings us to one of the most intriguing and, in recent years, most seriously discussed variations on the theme. The possibility that advanced civilizations do not spread outward across the galaxy in ships at all, because expansion of that kind is enormously expensive and slow and dangerous, and that instead, once a civilization reaches a certain level, it turns inward, retreating into vast virtual worlds of its own creation. Simulated reality so rich and so satisfying that the physical universe, with its slow light and its cold distances and its scarce resources, holds no further appeal. A civilization that has mastered computation might find that the most rational use of its resources is not to conquer the stars, but to build ever more elaborate inner universes, and to live there in simulated paradises tailored to their desires, indifferent to the empty galaxy outside. If this is a common destiny for intelligence, then the reason the sky is silent is that everyone who could be out there has chosen instead to be in there, absorbed in realities of their own making. No more interested in colonizing barren planets than we would be interested in colonizing a lifeless desert when a paradise is available at home. The great silence in this reading is not the silence of death or of absence, but the silence of a species that has simply gone quiet by choice, having found something better to do than shout into the dark. And there is a further dizzying extension of this idea that we cannot avoid mentioning, because it has been taken seriously by serious people. The possibility that reality itself, the reality you are experiencing right now, is one of those simulations, that we are the inner world of some vaster civilization, and that the reason we detect no other minds is that this particular simulation was simply not populated with them, that the empty galaxy is a stage set, elaborate but unfinished, containing only the one civilization the simulation was designed to run. We will not go all the way down that particular corridor tonight, because it leads somewhere the tools of science cannot presently follow. But it is worth pausing to notice how the Fermi Paradox, pushed hard enough, cracks open questions about the fundamental nature of reality itself, and how a simple lunchtime remark about the absence of aliens can, if you pull on the thread long enough, unravel your certainty about the ground beneath your feet. To think clearly about advanced civilizations, the ones that should have filled the galaxy and did not, it helps to have a way of measuring advancement itself, a scale against which to place both ourselves and the hypothetical others. In 1964, a Soviet astronomer named Nikolai Kardashev proposed exactly such a scale, and it has shaped the way we think about cosmic civilizations ever since. Kardashev reasoned that the single most useful measure of a civilization's advancement is not its art or its philosophy or its social organization, all of which are difficult to compare across species, but something far more universal and far more measurable, the amount of energy it is able to harness and control. Energy is the currency of all activity, biological, technological, cosmic, and a civilization's capabilities are ultimately bounded by how much of it they can command. So Kardashev drew a scale with 3 great rungs. A Type 1 civilization is one that has mastered all the energy available on its home planet, all the sunlight falling upon it, all the power of its winds and tides and geological heat, the total energy budget of an entire world brought under intelligent control. A Type 2 civilization has outgrown its planet and mastered the energy of its entire star, capturing not just the fraction of sunlight that happens to strike its homeworld, but the total output of the star itself, every photon streaming in every direction, perhaps through the great Dyson structures we spoke of earlier. And a Type 3 civilization has outgrown even its star and commands the energy of an entire galaxy. hundreds of billions of stars harnessed to its purposes. A civilization spread across the whole vast wheel of the Milky Way, wielding power on a scale that beggars imagination. Now here is the sobering part, the part that puts our own pretensions in perspective. On this scale, where do we sit? We who have split the atom and walked on the moon and built machines that think. We are not yet even a Type 1 civilization. We have not yet mastered the energy of our own planet. We are, by careful estimate, somewhere around Type 0.7, still climbing toward that first rung, still drawing most of our power from the buried remains of ancient life, still fumbling toward the mastery of our own world's energy, let alone our stars or our galaxies. We are cosmic infants, barely stirring, and yet even we, in our infancy, have begun to broadcast our presence to the stars and to dream of reaching them, which makes the absence of the others all the more striking. Because consider what a Type 3 civilization would mean. A civilization that has harnessed the energy of an entire galaxy would be, almost by definition, spread across that galaxy, present at hundreds of billions of stars, reshaping worlds and suns on a scale that could hardly be hidden. If even one Type 3 civilization had ever arisen in the Milky Way at any point in its billions of years of history, the galaxy should bear the unmistakable marks of it, and we should see those marks the moment we looked. And yet we look and we see a galaxy that appears, as far as our instruments can tell, entirely natural, entirely untouched. It's hundreds of billions of stars burning away in patterns that require no intelligence to explain. There is no Type 3 civilization in our galaxy that we can detect. There may be no Type 2 either. No star wrapped in the structures of a stellar-scale engineering project, at least none close enough or obvious enough for us to have found. The galaxy looks, to our best observation, like a wilderness, vast and beautiful and empty of the great works that advanced civilizations should inevitably produce. And this is itself a clue, and a troubling one, because it suggests that either civilizations very rarely climb the Kardashev scale to its higher rungs, or that something stops them before they can, or that they climb it in ways we cannot recognize, retreating perhaps into those inner virtual worlds, or transforming themselves into forms that leave no visible trace on the galactic canvas. The empty wilderness of the sky is not neutral, it is data. It tells us that whatever civilizations may arise, they do not, as a rule, blaze their way up the Kardashev scale and stamp their presence across the stars, because if they did, we would see it, and we do not. And this returns us, by yet another road, to the same crossroads we keep arriving at from every direction. The question of whether the barrier that keeps the galaxy quiet is one that civilizations rarely reach, or one that reliably destroys them, or one that transforms them into silence. There is a further wrinkle worth pausing on, which is the question of why a civilization would expand across the galaxy at all. Because the entire paradox rests on the assumption that they would, and that assumption deserves scrutiny. We assume that advanced civilizations spread, colonize, multiply, because that is what life on Earth does, what our own species has done, driven by the deep evolutionary imperatives of growth and competition and the search for resources. But it is possible that these imperatives, which feel so fundamental to us, are not universal, that they are quirks of our particular evolutionary history rather than laws that bind all intelligence everywhere. A civilization that has achieved stability, that has curbed its own population growth, that has learned to live within its means and find fulfillment without endless expansion, might feel no urge whatsoever to spread across the stars, might regard the whole project of galactic colonization as pointless, wasteful, even monstrous. Perhaps the civilizations that survive the longest are precisely the ones that learn to stop growing, that master the art of contentment, that turn away from the relentless expansion that characterizes younger and more aggressive cultures. And if that is so, then the galaxy might be full of quiet, stable, satisfied civilizations, each content to remain at home, tending its own star, uninterested in conquest or colonization or contact. And the silence would be the silence not of absence or death, but of maturity, of a galaxy full of grown-ups who have simply outgrown the childish desire to spread their name across every world within reach. Now we arrive at the explanations that are less about physics and distance and more about choice, about the possibility that the silence is not accidental at all, but deliberate, imposed, a quiet that is being actively maintained by minds that have decided, for reasons of their own, that we should not hear them. These are the explanations that shift the paradox from the realm of astronomy into the realm of psychology and strategy, and, in the darkest version, fear. And they are the ones that tend to linger with people long after the video ends. The first of these is called the zoo hypothesis, and it proposes something almost tender in its implications, though also faintly unsettling. It suggests that the galaxy is indeed inhabited, that advanced civilizations are aware of us, watching us perhaps, but that they have deliberately chosen not to make contact, the way the staff of a wildlife preserve observe the animals without interfering, allowing them to develop naturally, undisturbed in their own habitat. Under this hypothesis, there exists some kind of agreement, some galactic understanding, that young and emerging civilizations like ours should be left alone, quarantined, allowed to mature on our own terms, without the overwhelming and possibly destructive influence of contact with beings vastly more advanced than ourselves. We are, in this reading, a protected species, or an experiment being allowed to run, or simply a culture too primitive to be worth talking to yet. And the silence is a kind of courtesy, or a kind of caution, or a kind of patience. The older civilizations waiting for us to reach some threshold of maturity before they reveal themselves. It is an appealing idea in some ways because it preserves the possibility of a rich and living galaxy while explaining the silence, and it flatters us slightly by suggesting we are being watched over. But it has a serious weakness, which is that it requires an almost impossible degree of coordination and unanimity. For the zoo to work, every single civilization capable of contacting us, across the entire galaxy and across all of history, would have to agree to maintain the silence, without a single defector, without a single rogue individual or faction breaking the embargo, and holding that kind of perfect discipline across thousands of independent civilizations over millions of years strains belief. It only takes one to break the silence, and the silence is unbroken, which suggests either that there is no one there to break it, or that the reason for the silence is far stronger and more universal than mere etiquette. And that thought, the search for a reason so powerful that it would silence every civilization without exception, leads us to the darkest answer of all, the one that has burrowed its way into the popular imagination in recent years and refuses to leave because it is logical and cold and horribly plausible. It is called the dark forest hypothesis, and it reframes the friendly, curious, exploratory picture of alien contact that we have absorbed from a century of optimistic science fiction into something far more sinister. A picture in which the correct and rational behavior for any civilization is not to broadcast, not to explore openly, not to reach out, but to hide, to stay silent, and to destroy anyone foolish enough to reveal their position. The logic of the dark forest rests on two grim assumptions. The first is that every civilization, at its core, wants to survive. That survival is the fundamental drive of any life that has been shaped by the ruthless logic of evolution. The second is that resources in space, even in a universe this vast, are ultimately finite, and that civilizations grow, and that growth eventually brings them into competition. Now add to these two assumptions the profound and unavoidable problem of distance and time that we discussed earlier. If you detect another civilization, you cannot know their intentions. You cannot ask them, wait for the answer, and trust it, because any conversation takes decades or centuries or millennia to complete, and in that time the other side could advance enormously, could change, could become a threat you cannot anticipate. You cannot know whether they are benevolent or hostile, and you cannot afford to guess wrong, because if you guess that they are friendly and you are wrong, the price is annihilation. In this situation, game theory delivers a chilling conclusion. The safest course of action when you detect another civilization whose intentions you cannot verify and whose future capabilities you cannot predict is to destroy them preemptively before they can destroy you, and to do so silently without warning before they even know you exist. And if every civilization reasons this way, and the logic suggests that any civilization that does not reason this way is eventually eliminated by one that does, then the galaxy becomes a place of universal, mutual, silent terror. A dark forest in which every civilization is a hunter, moving as quietly as possible through the trees, aware that the forest is full of other hunters, and that to make a sound, to reveal your position, to broadcast your existence to the stars, is to invite a shot from the darkness, a shot you will never see coming, from an enemy you will never meet. In such a universe, the silence is not the silence of absence. It is the silence of predators, all of them holding their breath, all of them listening, all of them ready to strike. And the terrible implication is that our own behavior, our cheerful broadcasting of radio and television into the cosmos for the last century, our deliberate transmission of messages announcing our location and our nature to the stars, may be the most dangerous thing our species has ever done. A child shouting in a dark forest full of things with teeth. And if the dark forest is real, then we may have already made a fatal mistake, one whose consequences are simply still in transit, crossing the light years toward us, invisible, patient, and irreversible. It is a bleak vision, and it may not be true, and there are reasons to doubt it. Arguments that the economics of interstellar warfare do not favor such preemptive strikes, that a truly advanced civilization would have little to fear from a young one, and less to gain from destroying it, that the dark forest depends on assumptions about scarcity and hostility that may not hold. But it cannot be dismissed, because it follows so cleanly from premises that are hard to reject, and because it explains the silence better than almost any other single idea, and because there is a version of the reasoning behind it that any strategist, human or alien, would recognize. The dark forest may be wrong, but if it is right, then the safest thing we could possibly do is exactly what the galaxy appears to be doing, which is to say nothing at all. And the silence we hear is the sound of 100,000 civilizations, all of them wisely, fearfully, keeping quiet, and us in our innocence, doing the one thing that none of them would dare. It is worth slowing down and looking closely at the handful of moments in our brief history of searching when the silence seemed, for a little while, to break, when some signal or some object appeared that made scientists sit up and wonder whether, at last, they had found something. Because these episodes reveal both how much we long for an answer and how careful we must be in evaluating what we find. The most famous of these moments occurred on the 15th of August, 1977, at a radio observatory in Ohio. A telescope nicknamed the Big Ear that was patiently scanning the heavens as part of an early search for extraterrestrial signals. The telescope recorded its data as strings of numbers and letters representing signal intensity, and for the most part, these readings showed nothing but the low murmur of cosmic background noise. But on that August night, the telescope swept across a point in the constellation Sagittarius and recorded something extraordinary. A signal so strong, so narrow, so precisely the kind of transmission that a search for intelligence was designed to find, that when the astronomer Jerry Amon reviewed the printout a few days later, he was so startled that he circled a sequence of characters in red pen and wrote beside it, in the margin, a single word: wow. And so it has been known ever since, the wow signal, one of the most tantalizing near misses in the history of science. The signal lasted 72 seconds, which was exactly how long the telescope's field of view would take to sweep across a fixed point in the sky, exactly what you would expect from a genuine source out in space, rather than some local interference. It appeared at a frequency very close to one that many scientists had predicted would be a natural choice for interstellar communication, a frequency associated with hydrogen, the most common element in the universe, a kind of natural channel that any civilization might think to use. Everything about it looked right. And then it was gone. And despite many attempts over the following years and decades to detect it again, to point telescopes back at that same patch of sky and listen for a repeat, it has never returned. A single, unrepeatable, unexplained event hanging in the record like a question that was asked once and never answered. Scientists have proposed various natural explanations over the years, and some remain plausible, but none has been confirmed, and the wow signal endures as a genuine anomaly, neither proven to be alien nor explained away. A reminder of how a single moment of possibility can haunt a science for generations. Then there is the strange case of a star, cataloged with a long string of numbers, but known popularly by the nickname of the astronomer whose team drew attention to it. A star whose behavior, when first observed, was so bizarre that it briefly became the most talked about star in the galaxy, because one of the explanations seriously proposed for its strangeness was that it might be surrounded by the megastructures of an alien civilization. The star's light, observed over long periods by a space telescope designed to detect the tiny dimmings caused by planets passing in front of their stars, did something no planet could explain. It dimmed irregularly, dramatically, by amounts far too large to be caused by any planet, sometimes losing a fifth or more of its brightness in patterns that followed no regular schedule, that made no obvious sense. Something big and irregular and unpredictable was passing in front of that star, blocking its light in ways that ordinary astronomy struggled to explain. And for a while, one hypothesis on the table, discussed seriously by serious astronomers, was that we might be looking at a partially completed Dyson swarm, a vast array of structures built by an advanced civilization to capture their star's energy, the very megastructures that Freeman Dyson had imagined decades before. It was an electrifying possibility, and it drew intense scrutiny, telescopes around the world turning to watch this one peculiar star, searching for any additional sign of artificiality, any radio emission, any further clue. And in the end, the most likely explanation turned out to be natural, though still fascinating. Most probably an uneven cloud or rings of dust orbiting the star, blocking its light in irregular patterns, a natural phenomenon rather than an engineered one. But the episode was instructive because it showed how the scientific community actually responds to such anomalies, not with either credulous excitement or dismissive mockery, but with intense, careful, open-minded investigation, taking the extraordinary hypothesis seriously enough to test it rigorously, and following the evidence to wherever it led, which in this case was toward dust rather than aliens, but which might someday lead somewhere else. And then there was the visitor, the first object ever detected passing through our solar system that came from beyond it. From interstellar space, a genuine emissary from another star system, discovered in 2017 as it was already on its way out, having swung past the sun and begun its journey back into the darkness between the stars. It was given a name from the Hawaiian language, meaning a scout or messenger from afar, and it was strange in several ways that provoked intense discussion. It was oddly shaped, apparently far more elongated than any asteroid or comet we had seen, tumbling as it went, and it behaved in a manner that puzzled astronomers, appearing to accelerate slightly as it departed in a way not fully accounted for by the sun's gravity alone. Most scientists concluded that it was a natural object, a fragment of rock or ice ejected long ago from some distant planetary system, wandering the galaxy for perhaps billions of years before happening to pass through our corner of it, and that its odd acceleration could be explained by the gentle push of gas venting from its surface, a natural comet-like process. But a small number of respected scientists pointed out that its behavior was unusual enough to at least raise the question of whether it might be artificial, a piece of technology from another civilization, a probe, or the discarded fragment of one. And while this remained a minority view and the evidence favored a natural origin, the episode again demonstrated the proper scientific attitude, which is to keep the strange possibility on the table, to investigate rather than dismiss, and to acknowledge honestly the limits of what we know. What all these episodes share is a common lesson. We have so far found nothing that we can confirm to be evidence of another civilization. Every anomaly on close investigation has either yielded a natural explanation or remained simply unexplained, neither confirmed nor refuted. But we have also learned that when something genuinely strange appears, the scientific community does take it seriously, does investigate it rigorously, does consider the possibility of intelligence among the hypotheses to be tested. The search is real, the openness is real, and if a genuine signal ever does arrive, if some future anomaly resists all natural explanation and reveals the unmistakable fingerprint of another mind, we will know how to recognize it because we have been practicing, refining our methods on these near misses and false alarms, learning to tell the difference between the noise of the universe and the possible voice of another. So far, every voice we thought we heard has turned out to be an echo of our own hopes, or a natural process wearing an unfamiliar mask. But the listening continues, more sensitive and more thorough with each passing year. And the next anomaly, or the one after that, might be the one that does not go away. There is a question buried inside all of this that we have circled but not confronted directly. And it is a question we, as a species, are actually facing right now. Not in theory, but in practice. And it divides thoughtful people sharply, and it may be one of the most consequential decisions our civilization ever makes. Should we announce ourselves? Should we deliberately broadcast our existence to the stars, sending powerful, intentional messages designed to be detected by any civilization that might be listening? Or should we stay quiet, listen rather than speak, and reveal nothing about ourselves until we understand far better what might be out there? This is not an abstract debate. We have already, both accidentally and deliberately, been announcing ourselves for decades. Every radio and television broadcast our civilization has ever made has leaked out into space at the speed of light. An expanding bubble of our own signals now more than 100 light years across, carrying the noise of our civilization outward in all directions. A sphere of human chatter washing over thousands of nearby star systems, announcing to anyone with the sensitivity to detect it, that a technological species has arisen on this small blue world. Though it is worth noting that these leaked signals are faint and grow fainter with distance, and may be difficult to detect and harder still to interpret across interstellar distances. So our accidental broadcasting may be less revealing than it first appears. But we have also, on a handful of occasions, done something far more deliberate. We have aimed powerful transmitters at the stars and sent intentional messages, crafted to be recognizable as artificial, designed to announce our presence and share something of who we are. The most famous of these was sent in 1974 from a great radio telescope, a message beamed toward a distant cluster of stars, encoding in a pattern of pulses some basic facts about our chemistry, our biology, our solar system, our numbers. It was, in part, a demonstration, a proof of concept, but it was also a genuine message in a bottle, cast into the cosmic ocean. And it is out there now, traveling, and will arrive at its target in some tens of thousands of years, long after everyone who sent it, and quite possibly the entire civilization that produced it, has passed into history. This practice of deliberately transmitting messages to the stars has a name, sometimes called active searching or messaging to extraterrestrial intelligence, and it is deeply controversial because it raises exactly the danger that the dark forest hypothesis warns of. Those who oppose it argue, with considerable force, that we know nothing about what might be out there, that we cannot assess the risks, that broadcasting our location and nature to unknown recipients whose intentions we cannot fathom is an act of reckless and possibly suicidal naivety, a child shouting in the dark forest. They point out that the decision to reveal our species to the cosmos is one that affects all of humanity, present and future, and that no small group of scientists or enthusiasts has the right to make it unilaterally on behalf of everyone. That such a momentous choice should be made, if at all, only after the broadest possible deliberation, with full awareness of the stakes. Those who favor active messaging respond that the danger is overstated, that any civilization advanced enough to pose a threat to us across interstellar distances could almost certainly already detect our presence through our leaked signals and the chemical signatures of our living world, so that hiding is futile and the horse has already left the barn. They argue further that the potential benefits of contact, the knowledge, the perspective, the sheer wonder of no longer being alone, outweigh the speculative risks, and that a civilization that hides in fear forever will never grow, never learn, never take the leap that connection requires. And some argue, more philosophically, that if the dark forest is real, if the universe truly is a place where the rational strategy is silence and preemptive destruction, then perhaps it is better to know that, better to force the question than to huddle forever in fearful ignorance. It is a genuine dilemma without a clear answer, and it sits at the intersection of science and ethics and existential risk, and reasonable people disagree about it with great intensity. What it reveals is that the Fermi Paradox is not merely a question we observe from the outside, a puzzle about others. It is a question we are inside of, a question about our own behavior and our own choices, because we are ourselves one of the civilizations whose actions the paradox is about. Every choice we make about whether to broadcast, whether to listen, whether to expand, whether to survive, is a data point in the very question we are trying to answer. And future civilizations, if there are any, watching their own skies and asking their own version of Fermi's question, may one day factor our choices into their calculations, may detect our signals or our silence and draw their own conclusions about what kind of civilization we were and whether we survived. We are not just observers of the cosmic drama, we are actors in it, and the role we choose to play, loud or quiet, bold or cautious, expansive or contained, is being written now by us in this century, in these decades, perhaps in these very years. And that thought carries us toward the most sobering dimension of the entire question, the dimension that transforms it from a fascinating intellectual puzzle into something with the most immediate and personal stakes imaginable. The question of our own survival and whether the silence we hear is, in the end, a prophecy of our own fate. Return with me, one last time, to the darkest and most personally urgent interpretation of the silence, the possibility that the great filter lies not behind us, but ahead, and let us look at it not as an abstraction, but as a concrete question about the century we are living through. Because if this interpretation is correct, then understanding it may be, quite literally, a matter of survival for our species. The logic, recall, is this: if the early steps towards civilization, the origin of life, the emergence of complex organisms, the development of intelligence, turn out to be relatively common, then the reason the galaxy is silent must be that the later steps are where civilizations fail. And the latest step of all, the one we are approaching now, is the transition from a young technological civilization confined to a single planet into a mature one, capable of spreading beyond its home world and thus surviving whatever catastrophes might befall any single planet. That transition is a gauntlet, and it may be that no one, in all the history of the galaxy, has ever made it through, that every civilization that reaches roughly our level of development destroys itself, or collapses, or stagnates, or is destroyed before it can secure its future among the stars. And when we look honestly at our own situation, at the specific dangers that a civilization at our stage of development faces, the possibility that this is the filter becomes uncomfortably plausible, because we can see, in our own history and our own present, the outlines of several ways it might happen. Consider the danger we have already lived with for the better part of a century, the existence of weapons capable of destroying our own civilization. Within a stunningly short time after learning to harness the atom, our species built enough nuclear weapons to end itself many times over. And for decades, those weapons stood ready, held back only by the fragile restraint of human judgment. And there were moments, more than one, when that restraint very nearly failed, when the world came within a hair's breadth of nuclear war through misunderstanding, malfunction, or the terrible logic of confrontation. We survived those moments, but survival was not guaranteed, and the weapons remain, and the danger has not passed. It is entirely conceivable that many civilizations, upon developing advanced technology, likewise develop the means of their own destruction, and that the window between acquiring that power and acquiring the wisdom to manage it safely is a period of maximum danger through which many, or most, or perhaps all, fail to pass. Consider, too, the subtler danger of a civilization altering its own planet in ways that undermine the conditions for its survival, consuming resources faster than they can be replenished, changing the climate and chemistry of its world, degrading the very environmental stability that allowed it to flourish. Until the foundations of its civilization crumble, we are at this moment conducting exactly such an experiment on our own world, and we do not yet know how it will end, whether we will find the wisdom and the will to change course in time, or whether we will follow the trajectory that so many warn of, into decline and disruption and possibly collapse. Perhaps this is a common fate. Perhaps the same restless ingenuity that drives a species to build a technological civilization also drives it to consume and expand and exploit until it exhausts the world that sustains it. And perhaps that pattern is so deeply rooted in the evolutionary origins of intelligence that it plays out again and again on world after world. Each civilization burning bright and brief and then guttering out, having fouled its own nest beyond repair. Consider also the emerging dangers, the ones we can barely see the shape of yet, the powerful new technologies whose risks we are only beginning to understand, technologies that grant enormous power to those who wield them and whose misuse or malfunction could threaten civilization in ways we cannot fully anticipate. A civilization at our stage may face a proliferating array of such dangers, each new capability bringing new risks, and it may be that navigating this proliferation, threading the needle between the immense benefits and the catastrophic risks of ever more powerful technologies, is precisely the challenge at which civilizations fail, the reef on which they run aground. What all these dangers share is that they are, in a sense, self-inflicted. They are not asteroids or supernovae or cosmic catastrophes imposed from outside. They are the consequences of a civilization's own success, of the very power and ingenuity that let it rise, turned against it. And that is what makes the survival filter so plausible and so frightening, because it suggests that the seeds of destruction are planted in the same soil as the seeds of greatness, that the qualities which allow a species to build a civilization, its cleverness, its ambition, its drive to grow and expand and reshape the world, are the very qualities that, taken far enough, destroy it. If that is true, then the filter is not something rare and external that most civilizations happen to avoid. It is something universal and internal that most civilizations cannot escape, because it arises from their own nature, and we are subject to the same nature, and we are approaching the same reef. But here is the crucial point, the reason this interpretation should provoke not despair, but resolve. If the great filter lies ahead of us, if it is a challenge of survival and wisdom rather than an accident of chemistry or biology, then it is a challenge we might, in principle, meet. We cannot go back and change whether the origin of life was easy or hard. We cannot alter the improbability of the steps that lie behind us. But the steps ahead of us, the challenges of managing our technology, of stewarding our planet, of building a civilization that can survive its own power and eventually secure its future beyond a single vulnerable world. Those are challenges we can actually influence through our choices, our institutions, our wisdom, our will. If the filter is ahead, then it is not fate. It is a test, and tests can be passed. And perhaps that is the deepest meaning we can draw from the silence of the stars. Not a prophecy of doom, but a warning and a call, an invitation to become the civilization that beats the odds, that sees the reef and steers around it, that breaks the pattern of self-destruction and becomes, at last, the first to make it through, the first to spread beyond its cradle world and secure the flame of consciousness against the darkness. If every civilization before us has failed at this hurdle, then the galaxy is waiting, has been waiting for billions of years, for the first one to succeed, and there is no reason, in principle, why that first one could not be us. The silence does not have to be a graveyard. It could be an empty stage, waiting for someone, finally, to walk out onto it and refuse to fall. We have looked at the possibility that no one is out there, and at the possibility that they are out there but unseeable, and now we turn to the third and final camp, the strangest of the three, which proposes that they have been here, or are here, and that the evidence is either overlooked or misinterpreted, or has simply not yet been found in the vast and largely unexplored reaches of our own solar system. This camp does not require us to abandon science or embrace conspiracy. It requires only that we take seriously an idea that follows quite naturally from the mathematics of galactic colonization, the idea of the self-replicating probe. Recall that a civilization does not need to travel the galaxy in person to fill it with their presence. They need only build a machine capable of traveling to a nearby star, gathering raw materials there, and using those materials to build copies of itself, which then travel onward to the next stars and repeat the process. These are sometimes called von Neumann probes, after the mathematician who first rigorously described such self-replicating machines, and their power lies in exponential growth. One probe becomes two become four become 8, and within a span of time that is, again, cosmically brief, a single civilization could see the entire galaxy with billions of these machines, At least one in every solar system, quietly gathering information, perhaps waiting, perhaps observing, perhaps dormant for eons until triggered by some event. The unsettling implication is this: if self-replicating probes are possible, and they appear to be possible in principle, even for a civilization only modestly ahead of us, then the galaxy should be saturated with them. And that means there could be such a probe in our own solar system right now, and we might never have noticed it because our solar system is enormous and almost entirely unexplored. We have landed spacecraft on a handful of bodies, photographed a few dozen more, and left the overwhelming majority of the asteroids, moons, comets, and dark reaches of the outer system completely unexamined. An artifact the size of a car, or a building, or even a small moon, sitting quietly in the asteroid belt or in the shadowed craters of some distant moon, could have escaped our notice entirely, simply because we have never looked or never looked closely enough at the right place. When people imagine searching for evidence of alien visitation, they imagine dramatic encounters. But the more likely form of contact, if it exists, would be an ancient, silent, possibly long-dead machine. A piece of technology that arrived millions of years ago, did whatever it came to do, and has been sitting in the dark ever since, indistinguishable to our current instruments from an ordinary rock. This is not a claim that such a probe exists. It is a recognition that we have not remotely searched enough to rule it out, and that the absence of any confirmed detection tells us far more about the limits of our exploration than about the actual contents of our solar system. And here we should confront, briefly and carefully, the matter of the unexplained aerial phenomena that governments have in recent years begun to acknowledge and investigate more openly than before. It is important to be sober and scientific about this. The vast majority of such sightings have ordinary explanations: aircraft, atmospheric effects, sensor errors, and there is at present no verified scientific evidence that any of them represent visitors from another world. Extraordinary claims require extraordinary evidence, and that evidence has not been presented. But it is equally important not to dismiss the underlying question with a reflexive sneer, because the honest scientific position is one of humility, an acknowledgement that there remain phenomena we have not fully explained, and that a mature civilization investigates the unexplained rather than mocking those who point to it. The truth, whatever it is, will be found through patient observation and rigorous evidence, not through either credulous belief or contemptuous denial. And for now, the intellectually honest stance is to say that we do not know, that the question remains open, and that open questions are not embarrassments but invitations. Let us now turn to an explanation that is, in its own quiet way, as profound as any we have discussed, and which has gained considerable ground among scientists in recent years, because it flows from our improving understanding of the history and future of the universe itself. It is the possibility that we are not late to the party, as the timing problem might suggest, but early, extraordinarily early, among the very first guests to arrive. This idea rests on a fact about the universe that is easy to overlook, which is that the cosmos is, in the grand scheme of things, still young, and that the conditions for life may be improving rather than fading. The universe is 13.8 billion years old, but the stars that are best suited to hosting long-lived, stable, life-bearing planets, the small, cool, incredibly long-lived red dwarf stars that make up the majority of all stars in the galaxy, can burn steadily for not billions but trillions of years, 10 times, 100 times longer than the universe has so far existed. From the perspective of cosmic time, the universe has barely begun. The overwhelming majority of all the star years that will ever exist, all the time during which planets will orbit stable suns and life will have the chance to arise, lies in the future, an almost inconceivably vast future stretching trillions of years ahead. If you imagine the entire habitable lifespan of the universe as a single human life of 80 years, then we are appearing on the scene when the universe is roughly 4 months old. We are not the stragglers arriving after the party has ended. We are among the first few guests arriving so early that the host has barely finished setting up. And if that is true, then the reason we see no one else is beautifully simple and strangely hopeful. There is no one else yet, or almost no one, because it is still so early in the history of the universe that intelligent life is only just beginning to emerge. And we happen to be among the very first to do so. In this reading, the great silence is not the silence of a graveyard or a dark forest or a zoo, but the silence of an early morning before the world has woken up. The quiet of being among the first to open our eyes in a universe that will, in the fullness of its trillions of years, eventually fill with minds and voices and civilizations, none of which have arrived yet because we are the pioneers, the elders to be, the ones whose descendants, if we survive, might one day be the ancient and advanced civilization that some future young species looks up and wonders about, asking their own version of the question, where is everybody? Not knowing that we were here first, waiting in the long quiet of the cosmic dawn. There remain a few explanations we have touched on only lightly, and they are among the most imaginative and, in a strange way, the most beautiful, because they propose that the silence is not a problem to be solved but a natural and even desirable outcome of the maturation of intelligence. That advanced civilizations fall silent not because they die, but because they change, in ways that take them beyond our ability to perceive. The first of these is the idea of transcendence, the possibility that intelligence, once it reaches a certain level, does not continue to expand outward into physical space, colonizing planets and building visible empires among the stars, but instead moves in a different direction entirely, upward or inward, into forms of existence that leave the physical galaxy largely untouched. We have already discussed the possibility of civilizations retreating into virtual worlds, but transcendence is a broader and stranger idea than that. It suggests that a sufficiently advanced civilization might transform itself so thoroughly, might merge so completely with its own technology, might reorganize itself at scales so small or so subtle that it effectively disappears from the kind of view we are capable of. Perhaps advanced intelligence shrinks rather than grows, packing itself into ever smaller and more efficient forms of computation. Because small is fast and efficient, and a mind that runs on tiny, dense, cold hardware could think millions of times faster than one spread across a galaxy, limited by the crawling speed of light between its distant parts. A civilization that valued the richness and speed of its inner life over the crude sprawl of physical territory might choose to become small and quiet and dense and invisible, a jewel of concentrated thought rather than a sprawling empire. And there could be such jewels scattered throughout the galaxy, each one containing more experience, more thought, more life in the meaningful sense than entire physical civilizations. And we would never know, because they would be too small and too silent and too strange for us to detect. And there is an even more specific and more haunting version of this idea, one that connects the fate of civilizations to the deep physics of the universe itself, and it is called the aestivation hypothesis. Aestivation is the biological term for a kind of summer dormancy, the way some animals sleep through periods of extreme heat, waiting for cooler and more favorable conditions to return. The aestivation hypothesis proposes that advanced civilizations might be doing something analogous, but on a cosmic scale and for a cosmic reason. The reasoning goes like this. If a civilization's ultimate goal is to think, to compute, to process information, to experience, then its capabilities are limited by a subtle feature of physics, which is that computation is more efficient at lower temperatures. The colder the environment, the less energy it costs to perform a given calculation, the more thought you can extract from a given store of resources. And here is the crucial fact. The universe is cooling. As it expands, it grows colder, and it will continue to grow colder for trillions upon trillions of years, approaching ever nearer to absolute zero in the unimaginably distant future. Which means that a civilization that wanted to maximize the total amount of thinking it could ever do, the total experience it could ever have, would be wise not to spend its resources now in the relatively warm and wasteful present, but to save them, to hoard its energy, to enter a long dormancy, and to wait, to sleep through the current era of the universe and awaken in the deep cold future, when computation will be vastly more efficient, when the same store of energy will buy millions or billions of times more thought than it can today. Under this hypothesis, the great civilizations of the galaxy are not dead, and not hiding out of fear, and not lost across the gulfs of space and time. They are asleep. They have gathered their resources, secured them, and entered a deliberate dormancy, waiting out the warm early ages of the cosmos, dreaming perhaps, or simply paused, set to awaken in a future so distant that the stars themselves will have largely burned out when the universe has cooled enough to make their awakening worthwhile. And in that reading, in the silence of the sky is the silence of a galaxy full of sleepers, of ancient and powerful minds who have chosen to sit out the present age, and who might not take kindly to being disturbed, and who will one day, in the far cold future, wake and stretch and resume a project of thought and experience on a scale we cannot begin to imagine. It is a strange and poetic idea, and it may well be wrong, but it illustrates how the Fermi Paradox connects to the very deepest questions about the nature and destiny of the universe. How a simple question about the absence of aliens opens, when you follow it far enough, onto vistas of cosmic time and the ultimate fate of intelligence in a dying cosmos. There is one more possibility in this family worth naming, gentler than the others, which is simply that advanced civilizations lose interest in us, and in expansion and in contact, not through fear or transcendence or dormancy, but through something like wisdom or contentment, or a shift in values we cannot predict. We assume that any civilization capable of contacting us would be curious about us, would reach out. But perhaps that assumption reflects our own youthful eagerness more than any universal truth. Perhaps a truly ancient civilization, having seen 1,000 young species emerge and clamor for attention, having learned everything it wishes to know about the patterns by which biology gives rise to mind, would regard a new technological species like ourselves the way we might regard an ant colony discovered in the garden, with mild and passing interest at most, not worth the effort of contact, not worth interrupting whatever vast and subtle projects occupy their attention. We imagine ourselves fascinating, the kind of discovery that would thrill any observer. But to a civilization millions of years old, we might be utterly ordinary, one more predictable flowering of intelligence on one more unremarkable world. Nothing they have not seen countless times before, nothing that warrants breaking their silence. The silence in this reading is neither hostile nor protective nor accidental. It is simply indifference, the vast disinterest of the truly old in the frantically new, and perhaps the loneliest possibility of all is not that we are alone, but that we are surrounded and beneath notice. To understand why this question grips us so deeply, why it has fascinated some of the finest minds of the last century and refuses to release its hold, it helps to place it within a much longer story. The story of how our species has slowly, painfully, and repeatedly been forced to revise its sense of its own importance in the cosmos. A story of successive demotions, each one humbling, each one resisted, each one ultimately accepted, and each one leaving us a little smaller and the universe a little larger. For most of human history, we believed ourselves to be at the center of everything. The Earth, it seemed obvious, stood motionless at the center of the cosmos, and the sun and moon and stars and planets all revolved around us. And this arrangement seemed to confirm our special status, our place at the heart of creation. Then came the first great demotion, when it was understood that the Earth is not the center of anything, that it is merely one planet among several, circling the sun, which does not revolve around us at all. We were moved from the center to the sidelines, one world among many, and this was resisted fiercely because it wounded our sense of significance. But eventually the evidence became undeniable, and we accepted it. Then came the next emotion, when it was realized that the sun itself is not special, not the center of the universe, but merely one ordinary star among the hundreds of billions in our galaxy. An unremarkable yellow star in an unremarkable position, far from any center, drifting in one of the spiral arms of a vast wheel of stars. And then the demotion after that, when it was understood that our galaxy, the entire Milky Way, which had once seemed to be the whole universe, is itself merely one galaxy among billions, one island of stars in an ocean so vast that our entire galaxy is reduced to a single point of light among countless others. Each of these steps stripped away another layer of our assumed importance, moved us further from any center, made us smaller against the immensity of what surrounds us. This long humbling has a name among scientists. It is called the Copernican principle, after the astronomer who set the process in motion, And in its general form, it is the idea that we should not assume ourselves to occupy any special or privileged position in the universe, that we are most likely typical rather than exceptional, ordinary rather than unique. And the Copernican principle has been an extraordinarily successful guide, correct at every step. Each time we assumed we were special, we turned out to be ordinary. And the principle would seem to suggest that we are ordinary in this respect too, that life and intelligence, like everything else about us, should be common, typical, unremarkable, that we are just one of many, one instance of a phenomenon repeated countless times across the cosmos. But here is where the Fermi Paradox delivers its strange and unsettling twist. Its challenge to the very principle that has served us so well. Because if the Copernican principle is right, if we are typical, if life and intelligence are common, then the galaxy should be full, and we should see evidence of others everywhere, and we do not. The silence seems to violate the Copernican principle, seems to suggest that we are, after all, special, unusual, perhaps unique. That in this one respect at least we are not typical but exceptional, not one of many but possibly one of few, or even one of one. And this creates a genuine tension at the heart of the question, a collision between the principle that has guided us so reliably and the observation that seems to contradict it. Either we are not typical, and the long humbling of the Copernican principle finally reaches its limit here, at the question of life, where it turns out that we are, against all expectation, rare and precious and perhaps alone. Or we are typical, and the silence has some other explanation, one of the many we have explored, distance or timing or transcendence or the dark forest or the filter, some reason why a galaxy full of others could still appear, to us, to be empty. The Fermi Paradox in this light is the place where our long journey of cosmic humility meets an obstacle, where the principle of our own ordinariness runs up against evidence that we might, after all, be extraordinary. And the resolution of that tension, whichever way it falls, will tell us something profound about our place in the scheme of things. If we are alone, then the demotions end here, and we are returned in a strange and sobering way to a kind of centrality, not because we are at the physical center of anything, but because we are, as far as we can tell, the only place where the universe has become aware of itself, the only eyes, the only mind, the only witness, and that is a kind of importance far heavier and more consequential than the naive centrality we once imagined. And if we are not alone, if the others are simply hidden or distant or silent, then the Copernican principle holds, and we take our place as one civilization among many, participants in a cosmic community we have not yet learned to perceive. And our task becomes not to bear the weight of cosmic loneliness, but to find our way into that community, to learn to see and hear our neighbors, to end the isolation, not of the universe, but of our own perception. It is worth pausing to appreciate the sheer strangeness of being the kind of creature that can even frame such a question, that can look up at the night sky and, from a scattering of points of light, reconstruct the size and age and structure of the entire cosmos, can calculate the number of stars and worlds, can reason about the probability of life and the fate of civilizations, can ask with genuine rigor whether it is alone. Whatever else we are the part of the universe that has learned to wonder about itself, and that capacity, that reflective awareness, is either extraordinarily rare, in which case we are precious beyond measure, or wonderfully common, in which case the universe is richer and stranger and more full of minds than we have yet been able to see. Both possibilities are staggering. Both should fill us with awe. And the fact that we do not yet know which is true, that the question remains genuinely open, that we are living in the very era when our species first became able to ask it seriously and might, within a generation or two, begin to answer it, makes this one of the most extraordinary moments in the entire history of our kind. A threshold moment, a moment of not knowing that is also a moment of beginning to find out. It would be easy, after wandering through all these possibilities, to conclude that the question is unanswerable, a matter for endless speculation with no hope of resolution. But that would be a mistake, because the remarkable truth is that for the first time in the history of our species, we are actually beginning to gather real evidence to move the question out of the realm of pure philosophy and into the realm of observation. And the coming decades may transform this entire discussion from a game of imagination into a genuine science with data and results. Let us talk about what we are actually doing right now to answer Fermi's question, because it is more than you might think, and it is accelerating. The oldest and most direct approach is the one Frank Drake began in 1960, listening for radio signals, and it continues today on a scale he could scarcely have imagined. Modern radio searches scan millions of stars across enormous ranges of the spectrum, using arrays of telescopes and sophisticated algorithms to sift through oceans of cosmic noise, hunting for any signal that bears the unmistakable stamp of intelligence, a narrow band transmission, a mathematical pattern, a repetition that nature does not produce. Privately funded initiatives have poured resources into this search, dedicating thousands of hours of telescope time and building software capable of analyzing signals at a scale never before possible. So far, the result is silence, punctuated by a handful of tantalizing anomalies that captured attention for a time before being explained or dismissed or simply left unresolved for lack of a repeat. There was famously a signal detected in 1977, so strong and so striking that the astronomer who spotted it circled the printout and wrote a single word beside it: wow. And that wow signal, as it came to be known, has never been explained and never been detected again, and a single, unrepeatable moment of possibility that hangs in the history of the search like an unfinished sentence. But radio is only one approach, and in some ways the search has moved beyond it into methods Drake could not have dreamed of. Consider the search for biosignatures, the chemical fingerprints of life itself, written in the atmospheres of distant worlds. We now possess telescopes capable of analyzing the light that passes through the atmosphere of a planet orbiting another star, splitting that light into its component colors and reading, in the pattern of what is absorbed and what is transmitted, the chemical composition of that distant air. And certain combinations of gases, certain chemical imbalances, are difficult to explain without life. Oxygen in large quantities, for instance, is highly reactive and tends to disappear from an atmosphere unless something is continuously replenishing it, as photosynthesis does on Earth. Find an atmosphere rich in oxygen or in other telltale combinations of gases that should not coexist without some process actively maintaining them, and you have found powerful, though not conclusive, evidence that something living is at work on that world. The newest generation of space telescopes is beginning to make exactly these measurements, and in the coming years we may, for the first time, detect the signature of life on a planet light years away. Not intelligent life necessarily, not a civilization, but life, the mere existence of which would transform everything, would tell us at a stroke that biology is not unique to Earth, and would, in the chilling logic of the Great Filter, push the deadly barrier one gate closer to our own future. Beyond biosignatures lies the search for technosignatures, the fingerprints not of life but of technology, and here the ideas become genuinely spectacular. If a civilization grows powerful enough, it may begin to reshape its environment on scales visible across interstellar distances. The physicist Freeman Dyson imagined that an advanced civilization, hungry for energy, might eventually build a vast structure or swarm of structures around its home star, capturing a significant fraction of all the energy that star produces. A construction so enormous it would enclose the star itself. Such a structure, now called a Dyson sphere or Dyson swarm, would betray itself in a peculiar way. The star's visible light would be dimmed or hidden, but the captured energy would eventually be radiated away as waste heat, as infrared, so that from a distance the star would appear strange, cooler than it should be, glowing in the infrared like a dying ember while producing the energy output of a healthy sun. Astronomers have actually searched for exactly this signature, scanning catalogs of stars for the telltale infrared excess that a Dyson structure would produce, and while a few candidates have raised eyebrows over the years, none has survived scrutiny, each one eventually yielding to a natural explanation. But the search continues, and it is a real search, conducted with real telescopes and real data, for the megastructures of civilizations that may or may not exist. And this points to something important about the entire enterprise, which is that the Fermi Paradox is no longer purely a thought experiment. It has become an observational science, with instruments and methods and results, and the pace of that science is quickening dramatically. We are building larger telescopes, both on the ground and in space. We are developing the ability to directly image planets around other stars, to map their surfaces, to read their atmospheres. We are cataloging the strange and the anomalous across the sky with unprecedented thoroughness. Within the lifetimes of many people watching this video, we may cross one of the great thresholds of human history, either by detecting the first genuine evidence of life beyond Earth, or by pushing the limits of our search so far, examining so many worlds and finding them so consistently barren that the silence itself becomes a kind of answer, a growing weight of evidence that whatever the explanation, life like ours is rare and precious and perhaps alone. Either outcome would be among the most profound discoveries our species has ever made, and we are, right now, in the early chapters of finding out which it will be. There is a human story woven through all of this, a story of the particular people who chose to devote their lives to a question that many of their colleagues considered unserious, even frivolous. A question with no guarantee of ever being answered, and their persistence and their vision deserve to be remembered, because the search for other minds in the cosmos is not only a scientific enterprise, but a deeply human one, an expression of our oldest longing not to be alone. We have spoken of Fermi, whose lunchtime question gave the paradox its name, and of Drake, whose equation gave it structure. But the search had other champions, and perhaps none did more to bring it into the public imagination, to make it respectable, to give it heart, than a young astronomer who would become one of the most beloved science communicators of all time. A man who understood, better than almost anyone, that the question of whether we are alone is not merely a technical matter of radio frequencies and probability estimates, but a question that touches something essential in the human spirit. Our sense of our place in the universe, our loneliness, our hope, our capacity for wonder. He argued passionately and eloquently that the search was worth undertaking, not only for what it might find, but for what it revealed about us, about our willingness to ask the largest questions, to reach beyond our small world, to imagine that we might not be the only ones. And he was involved in one of the most poignant gestures our species has ever made toward the possibility of cosmic companionship, the placing, aboard 2 spacecraft launched in the 1970s and destined to leave our solar system entirely and drift forever among the stars, of a message, a kind of greeting card to the cosmos, in case in some unimaginably distant future, some other mind should ever encounter these tiny wandering machines and wonder who had made them. The message took the form of a golden record, a phonograph record plated in gold to survive the eons, and on it was encoded a portrait of our world and our species. Sounds and images gathered to represent the whole of human experience, to an audience we would never meet and could scarcely imagine. There were greetings spoken in dozens of human languages. There were the sounds of our world, wind and rain and thunder, the songs of birds and whales, the sounds of a human heartbeat, of a mother speaking to her child, of laughter. There was music carefully chosen to represent the range and depth of human artistic achievement, from classical compositions to folk songs to the music of many cultures around the globe, a sampling of the beauty our species has created. There were images encoded in the grooves of the record, showing our anatomy, our diversity, our planet, our achievements, a visual introduction to who we are. And there was a map of sorts showing the location of our sun relative to certain distinctive cosmic landmarks, so that any finder might, in principle, trace the record back to its origin, might find their way to the small blue world from which this greeting had been launched into the dark. It was, in a sense, an act of hope against overwhelming odds, because the spacecraft carrying these records will not come near another star for tens of thousands of years. And the chance that either of them will ever be found by another intelligence is vanishingly small, so small as to be almost negligible. And yet we made them and launched them, and they are out there now, having crossed the boundary of our solar system, sailing on into the interstellar dark, carrying their golden greetings, their music and their heartbeats and their languages, into a silence that may never answer. There is something almost unbearably moving in that gesture. In a young species, uncertain whether it is alone, uncertain whether it will even survive, taking the time to craft a message of greeting and hope and beauty, and casting it into the cosmic ocean. Not because it expects a reply, but because the act of reaching out, the refusal to be silent, the insistence on saying, here we are, this is who we are, this is what we love, is itself an affirmation of everything that makes us worth finding. And there was another gesture, quieter but equally profound, when one of those same distant spacecraft, having completed its mission among the outer planets and sailing outward toward interstellar space, was commanded to turn its camera back one last time toward the home it was leaving and to photograph the Earth from a distance of billions of kilometers. In that photograph, our entire world, everything that has ever happened to anyone, every person who has ever lived, every civilization, every war, every love, every moment of every life, appears as nothing more than a single pale point of light. A tiny dot suspended in a sunbeam, smaller than a pixel, almost lost in the vastness. That image of our whole world reduced to a pale blue dot adrift in the immensity has become one of the most powerful and humbling images in the history of our species, because it shows with brutal and beautiful clarity exactly how small we are, how fragile, how alone, at least so far, in the great dark. And it carries within that smallness a message that connects directly to everything we have been exploring tonight. That pale blue dot is, as far as we know for certain, the only place in the entire universe where life exists, the only world that harbors anyone at all, and whether or not there are others out there in the silent dark. This one small dot is, for now, the only home we have and the only life we know, and its preciousness, its fragility, its solitary flicker of consciousness in an immense and silent cosmos, is precisely what the Fermi Paradox, in the end, forces us to confront. Whether we are alone or not, this world and the life upon it, and the minds that have arisen here capable of asking these very questions, are rare and precious beyond any reckoning. And the silence of the stars, whatever its true cause, teaches us above all to cherish and protect the one small pale blue point of light, where, against all the odds, the universe has awakened and looked around and begun to wonder. It is worth sitting for a moment with just how strange our situation truly is, because familiarity has a way of dulling the wonder of it, and this is a thing that deserves to be felt freshly. Right now, as you listen to this, you are on the surface of a spinning ball of rock and iron and water, hurtling around a star at more than 100,000 kilometers per hour. And that star is itself racing around the center of a galaxy at a speed hundreds of times greater, dragging you and everyone you have ever known along with it through a cosmos so vast that the light from the nearest large galaxy left its source before our species existed and is only reaching us now. And in all of that motion, across all of that distance, through all of that time, you have never once received a confirmed word from another mind that did not originate on this single small world. Not one. In the entire history of our species, across every civilization that has ever risen and fallen, across every telescope ever pointed at the sky, and every antenna ever tuned to the cosmic static, the total number of confirmed messages from another intelligence in the universe stands at 0. That is either the loneliest fact in all of human experience, or it is a temporary condition, a silence that will one day break, and we do not know which. And that not knowing is the very thing that makes this the most important open question we have ever been able to ask. Every other great mystery we have faced, we have eventually cracked open, at least a little, learned something, made progress, and this one alone, the question of whether we are alone, remains as open today as it was on that summer afternoon when Fermi first asked where everybody is, more urgent than ever, more answerable than ever, and still, for now, unanswered. And consider one further strangeness before we close, which is the peculiar position we occupy in time, poised at the exact moment when the question becomes askable. For all the tens of thousands of years that human beings have looked up at the stars, they could only wonder, could only invent myths and stories to populate the heavens, because they had no way of knowing what the stars truly were, How far away, how numerous, whether they had worlds, whether those worlds had life. That ignorance lasted almost the entire span of human existence. It is only in the last century, a mere flicker at the very end of our long history, that we have learned what the stars are, discovered the other worlds, built the instruments to listen, and framed the question in terms that admit of a real answer. We are the first generations of humans who could genuinely search, and we may be among the last who do not know the answer, because the pace of discovery is such that within a lifetime or two, we may cross the threshold from not knowing to knowing, may detect the first biosignature, the first technosignature, the first unambiguous sign that we are not alone, or may search so thoroughly and find so consistently nothing that the weight of the silence becomes an answer in itself. To be alive now, in this narrow window, aware of the question and living through the era when it might be resolved, is an extraordinary privilege and an extraordinary responsibility. Because whatever we learn, whichever way the answer falls, it will change forever how our species understands itself. And we are the ones who get to find out, or at least to begin to. So where does all of this leave us? We have walked through a great many doors, and behind each one waited a different universe. Behind the first door, the universe is nearly empty, and we are alone, or very nearly so, because the road from dead chemistry to a thinking mind is so long and so treacherous that almost nothing ever completes the journey, and our own existence is a fragile miracle, unrepeated across 100,000 light years. Behind the second door waits the great filter, and the question of whether the deadly barrier lies behind us, in which case we are the improbable survivors, or ahead of us, in which case we are speeding toward the same wall that has stopped every civilization before us. And the silence is a warning we do not yet know how to read. Behind the third door, the galaxy teems with life and even intelligence, but the gulfs of space and time are so vast, and the windows of detectability so brief, that no two civilizations ever quite reach each other, all of us calling out across distances too great and moments too fleeting, alone together in a crowded universe that feels empty only because we cannot bridge the space between one mind and another. Behind the fourth door, they are out there and could be seen, but they are so far beyond us, so incomprehensible, that we walk among the evidence of their existence and mistake all of it for nature. Ants on a highway, unable even to conceive of the beings whose works surround us. Behind the fifth door, they know we are here, and they are watching, and they have chosen silence, either out of a protective courtesy, letting us grow undisturbed, or out of a colder calculation. Hiding in a dark forest where to speak is to die. And behind the last door, the strangest and in some ways the most hopeful, we are simply early, among the very first minds to open their eyes in a universe still in its infancy, the pioneers of a cosmic morning that will, over the trillions of years to come, eventually fill with the voices we are listening for in vain, because they have not yet been born. Which of these is true? The honest answer, the only intellectually defensible answer, is that we do not know. Not yet, perhaps not for a very long time. But I want to suggest to you that not knowing is not the same as having nothing, because the question itself, held seriously, changes the way you see everything. When you truly absorb the scale of the silence, when you feel the weight of that empty sky and the enormity of what its emptiness might mean, something shifts in your understanding of your own existence and of the existence of this small, warm, improbable world beneath your feet. Because whichever answer is true, nearly all of them converge on a single practical conclusion, and it is this: life, and especially intelligent life, may be far more precious, far more fragile, and far more rare than our intuition suggests. And the survival of this one confirmed instance of it, our own, is not something to be taken for granted. If we are alone, then we carry the only known flame of consciousness in a dark and enormous cosmos, and to let it go out through carelessness or violence or short-sightedness would be a tragedy beyond all measure, the universe losing the only eyes it had grown to see itself with. And if we are not alone, if the great filter lies ahead of us, then the silence is a graveyard, and every quiet star is a warning. And the great question of our age is whether we can be the first, the very first in all the history of the galaxy, to see the wall coming and find a way around it, to break the pattern that has claimed everyone before us, to prove that intelligence and wisdom can, after all, coexist long enough to reach the stars. Either way, the lesson is the same. This moment, this civilization, this brief window in which we have become capable of asking the question and beginning to answer it, is extraordinary and precarious and worth protecting with everything we have. The Fermi Paradox in the end is not really a question about aliens. It is a mirror. We look out into the silent cosmos, hoping to find others, and what we find staring back at us is ourselves, our own fragility, our own improbability, our own uncertain future. The empty sky asks us who we intend to be, whether we will be the civilization that passed the final filter or the one that failed it, whether we will be a beginning or an end. And it asks us to notice, really notice. And behind the last door, the strangest and in some ways the most hopeful, we are simply early, among the very first minds to open their eyes in a universe still in its infancy, the pioneers of a cosmic morning that will, over the trillions of years to come, eventually fill with the voices we are listening for in vain, because they have not yet been born. Which of these is true? The honest answer, the only intellectually defensible answer, is that we do not know. Not yet, perhaps not for a very long time. But I want to suggest to you that not knowing is not the same as having nothing, because the question itself, held seriously, changes the way you see everything. When you truly absorb the scale of the silence, when you feel the weight of that empty sky and the enormity of what its emptiness might mean, something shifts in your understanding of your own existence and of the existence of this small, warm, improbable world beneath your feet. Because whichever answer is true, nearly all of them converge on a single practical conclusion, and it is this: life, and especially intelligent life, may be far more precious, far more fragile, and far more rare than our intuition suggests, and the survival of this one confirmed instance of it, our own, is not something to be taken for granted. If we are alone, then we carry the only known flame of consciousness in a dark and enormous cosmos, and to let it go out through carelessness or violence or short-sightedness would be a tragedy beyond all measure, the universe losing the only eyes it had grown to see itself with. And if we are not alone, if the great filter lies ahead of us, then the silence is a graveyard, and every quiet star is a warning. And the great question of our age is whether we can be the first, the very first in all the history of the galaxy, to see the wall coming and find a way around it, to break the pattern that has claimed everyone before us, to prove that intelligence and wisdom can, after all, coexist long enough to reach the stars. Either way, the lesson is the same. This moment, this civilization, this brief window in which we have become capable of asking the question and beginning to answer it, is extraordinary and precarious and worth protecting with everything we have. The Fermi Paradox in the end is not really a question about aliens. It is a mirror. We look out into the silent cosmos hoping to find others, and what we find staring back at us is ourselves, our own fragility, our own improbability, our own uncertain future. The empty sky asks us who we intend to be, whether we will be the civilization that passed the final filter or the one that failed it, whether we will be a beginning or an end. And it asks us to notice, really notice, the miracle of where we already are on a living world, under a sky full of stars, at a moment when we have just barely become capable of understanding what those stars are, and how far away and how silent, alive at the dawn of the only cosmic story we know for certain, includes anyone at all. That is not a small thing. That may be the largest thing there is. The stars will keep their silence, at least for now, and we will keep listening, keep searching, keep building better instruments and asking sharper questions. And perhaps within the lifetime of someone watching this, the silence will break and everything will change. Or perhaps it will not, and the quiet will deepen, and we will come slowly to understand that the responsibility for consciousness in this corner of the universe rests for now entirely with us. Either way, the next time you find yourself under a clear night sky, far from the city lights, look up at those 2,000 or 3,000 visible stars and remember that behind them lie hundreds of billions more, and behind those trillions of galaxies, And remember that somewhere in that vastness, the answer to Fermi's question is waiting, has always been waiting. Whether it is a universe full of silent hunters, or a graveyard of the fallen, or a nursery of minds not yet born, or a preserve in which we are the protected animals, or simply an empty immensity in which we are the only ones awake. And remember that you are alive at the moment when our species first became able to ask and to search, and perhaps one day to know. If this journey held you, if it made the sky look a little different, a little deeper, a little more charged with meaning and mystery, then do the 3 small things that help these journeys reach other minds like yours. Subscribe so you are here for the next descent into the strange and the vast. Like the video so the platform carries it further into the dark. And in the comments, along with the city and the hour you are watching from, tell me which door you believe hides the truth, which answer to the great silence you find most convincing, or most frightening, or most beautiful, because I read every one, and the conversation in those comments is, in its own small way, exactly the thing the whole universe seems to be missing. Minds reaching out to other minds across the dark, refusing to be silent, insisting against all the vast indifference of space on being heard. The stars are still up there, still silent, still waiting. And now at least you know the shape of the question they are asking. Sleep well.